Welcome to the chapter guide. Chapter 10 study guide. On this problem, you have to do a number of different things. No surprise there. You have to do more than one thing. Okay, so the first thing is we have to place the reactants and the products. Well, it's just, always reactants to products. So the first thing we run into, reaction pathway, another way you can think of this is time moving this direction. So we'll always start with reactants, and we always finish with products. The direction of the heat flow, in order to go from reactants to products, heat has to be put into the system. So delta H is positive. That makes it endothermic. And the extra credit, I'm going to leave you with an example of a chemical reaction that is endothermic. P.S. is what I was going to say. Hint, check your notes. You get to make a decision, and I'm going to do both of the choices that you have so you can see them clearly. You get to decide what is your system and what's the surroundings. Our first scenario would be this is the system, which makes the outside water the surroundings. And then we have to indicate the direction of heat flow. Remember, heat flow always goes from hot to cold. In this case, the heat flow goes from the system into the surroundings. The other way you could have done this is labeled this blue water as the system and the inside water as the surroundings. That would have been fine. You just have to indicate which is which. The direction of your heat flow is still going to go from hot to cold, always. So for this particular problem, your direction of heat flow is still going to be from the hot stuff into the cold stuff. This particular way of writing surroundings to system is, even though the heat flow is going from hot to cold, it's still going into the system. That makes it endothermic, the way I've drawn it. If you flip it like I did on the first slide, where the inside container is the system and the outside container is the surroundings, the heat flow still goes this direction, but now it's defined as exothermic because it's always going to be from the point of view of the system. It's leaving the system into the surroundings, therefore it's exothermic. On this finally picture, you need to estimate the final temperature. And if we assume that we have the exact same amount of water inside the system and outside in the surroundings, your final temperature is simply the average of these two numbers, or you could have called it the mean of these two numbers. It means the same thing, which gives us about 113 degrees Celsius. Remember, kinetic energy is another way we define temperature. Temperature is the average kinetic energy. So first off, hot water has faster moving molecules, or higher kinetic energy, than the container with the cold molecules. The hot water molecules are able to transfer their kinetic energy to the colder molecules, causing the colder molecules to speed up. This transfer will continue until all of the molecules are at the same average kinetic energy, which is the definition of temperature. If heat flows out of the surroundings, how would you describe this? In other words, is it exothermic or endothermic? And then justify your answer. Well, I would start off by drawing a picture showing both the system and the surroundings. And then we need an arrow. Heat flows out of the surroundings. That means if it's going out of the surroundings, it's going into the system. That means this process is endothermic. And to justify your answer, I would say because the heat flow, or you could say delta H, but the heat flow goes into the system. And a picture is worth a lot for understanding the direction of heat flow. A really good thing to solve these problems is write down what you have out of the problem before you try to solve the problem. So how many joules of energy? So joules is going to equal question mark. We have 250 grams of carbon. Well, I know that's mass of carbon. And we're going to change its temperature. Changing temperature, that should tell you immediately that we're going to use this formula because we're talking about a change in temperature. So we have a initial temperature of 26.6 degrees Celsius and we have a final temperature of 154.2 degrees Celsius. And there is the value of C, because we know C's units are joules per grams times degrees Celsius. So Q equals, well, Q is what we're after because that's in terms of joules, is equal to mass. We have the mass of 250 grams, and I'm going to omit units, and now put them in, times C. We have C is 0.71 joules per grams times degrees Celsius times our change in heat energy. Well, delta T is equal to the final minus the initial temperature. And I'm just going to go ahead and solve for that right now. After using the handy dandy calculator, 127.6 degrees Celsius. And the nice part about writing out the units is you can see that they do cancel out. The grams cancel, the degrees Celsius cancels, and we're left with the unit we want. Now we just have to multiply it all across. So we end up with a final answer of Q equaling 22649 joules. Our last step is to make sure we have the correct number of significant figures. Well, there's 3. Well, gosh, when we subtracted these two numbers, we should have had one decimal place. So that was 127.6. That has 4 sig figs. So our final answer should only have 3 significant digits. There's 2 ways you could do it. You could make this 22600 joules or 2.26 times 10, 4 joules. Either answer's fine. Again, you want to write out what you have from this problem. So we have a 300 gram sample of aluminum, so our mass is equal to 300 grams of aluminum at 25 degrees Celsius, so that's our initial temperature. And it absorbs 5.4 kilojoules. So Q is equal to 5.400 kilojoules. What's the final temperature? Again, we're dealing with a change in energy, so we're going to need Q equals MC delta T, and C was given to us right here in the problem. For this one, I want to substitute the delta T for Q is equal to MC temperature final minus temperature initial. But first, we're going to have to convert this kilojoules to joules. Notice your specific heat capacities in joules, so Q better be in joules also. So let's go ahead and convert that. 5.4 kilojoules. And for every 1 kilojoule, we have 1,000 joules. So that's 5.4 times 10 to the third joules. And it absorbed, so it'll definitely be positive. Q is positive. All right, now let's substitute. For Q, I'm going to put 5.4 times 10 to the third joules equals, now here comes the M, so we want 300 grams. Now we need the C, 0.89. Okay, so I'm dropping units. Now we need our final temperature, which we don't know, so we'll go ahead and call that X, minus, but we do know our initial temperature, so 25. And I'm going to go ahead and take those units out just so you can see the algebra a little more easily. The first thing you're going to want to do then is combine your like terms. So bring this down, 5.4 times 10 to the third equals, I'm going to multiply this number and this number together. So we end up with 267 times x minus 25. A lot of people want to distribute at this point, and you can do that. It'll just cost you one extra step. I would rather divide each side by 267. So when I do that, I end up with 20.2 equals x minus 25. Now we can simply add 25 to both sides. And we do need one decimal place because that has a decimal place, so we end up with 45.2 degrees Celsius will equal our final temperature. A really good idea is to write out what you have in each problem before you start the problem. All right, 1 mole of ethylene is burned at constant pressure. This much energy is released as heat. So we end up with negative 1410 kilojoules for every 1 mole of C2H4. That's what that first whole line says. We need delta H when we have 50 grams of ethylene. So we simply need to convert grams to moles to kilojoules. We're going to start off with the 50 grams. Of ethylene. Chase this unit down so we end up with grams of C2H2 to 1 mole. And then we're going to use this conversion, that 1 mole of C2H4. I keep writing that wrong. Interesting. Let's change those to 4 and to 4 and to 4. Negative 1410 kilojoules. Now I just need to find the molar mass of C2H4. So when I did that, I ended up with 28, somewhere I have a pen, there we go, 28.05 grams. Now I can do the final math, 50 times 1410 divided by the molar mass. So we end up with 2513 kilojoules of C2H4. Let's see, we have 3 sig figs there. We don't want to use this one for sig figs because that's like a constant, so we're not going to use that. So we need 3 sig figs, 2510 kilojoules of C2H4. This is a Hess's Law problem. And the first thing you're going to want to do is write down your goal equation. That's what you're after. Now, you're not going to use that to solve the problem. That's just sort of a reference. And take a look at the 3 equations that have been given to us. Well, I always like to start with the first reactant, this guy. Do you see him anywhere in these 3? Well, I see him right there. And he's already a reactant, so I can just write it as is. I don't have to flip it or anything like that. N2H4 plus CH4O yields Don't forget to make sure you keep track of your kilojoules. I'm going to write delta H up here in terms of kilojoules. Now look for an intermediate. Is there something in the yellow equation that does not appear in our goal equation? Well, there's a couple of things. So let's start with the CH4. I mean, why not? Doesn't go, so let's give it a start. Well, for starters, let's get rid of this guy. I'm not going to use him anymore. Let's go with this green start equation. Do I want to use it as is, or do I want to flip it? Yeah, I definitely want to flip it, because substances that appear on opposite sides of the arrows, the only way you're going to get them to cancel out. All right, H2 plus CH2O yields CH4O. Now I got to flip the sign, 65 kilojoules. Now let's add these guys up. I don't see N2H4 anyplace else, so I'm just going to bring it down. The CH4s, O's cancel. These two cancel. H2 appears there and there. That's going to be a product because I have more on the product side. So that's 2H2. Now I'm going to bring the N2 down. Don't forget to keep track of your delta H as you go, which is 28 kilojoules. We're done with this guy. How am I going to use our last equation to finish this problem up? Well, what is in the blue equation we don't want any in the goal? Well, that would be the nitrogen. The nitrogen does not appear in our goal equation. So how can I use the orange starred equation to get rid of it? I'm going to use it as is. So we have N2 plus 3H2 yields 2NH3 and negative 46. Your nitrogens cancel. 1 minus 1 is 1. N2H4, I don't see that anyplace else. 3H2s and 2H2s, well, those subtract, leaving me with 1 H2 on this side. And now I can bring my 2 ammonias down. Does that look like the goal equation? Well, yes, it does. Adding these guys up, we end up with negative 21 kilojoules as our final answer. Take some time, read through this problem. This is exactly like the lab that we did in class. The first part of this problem is going to ask that you use Q equals MCAT to find the amount of heat absorbed by your water. So we're solving for Q of the water. The mass, you should always write this down, Q equals MC delta T. The mass of the water is 200 grams times the specific heat of water multiplied by the change in temperature of the water. And just for sig fig purposes, I went ahead and subtracted these two to let me know that I end up with 13.4, which is 3 sig figs. The 200.0 is more than that, so we're going to need 3 sig figs in our final answer. So 200 times 4.184 times 13.4, 11213 joules. Now we need 3 sig figs, so that's 11200 joules, and we want to make sure it's positive because it's the heat absorbed by your water. Because you took a piece of hot metal and put it in cool water, where did the water get its heat from? Well, the heat of the water came from the heat of the metal. And in a perfect world, they would be exactly the same. And we're going to go ahead and make that assumption. The only difference is that when water absorbs heat, it's positive. And when the metal gave off heat, it's negative. It is the absolute value of these two numbers that's the same. The magnitude of the number is the same. It's the direction that is the opposite. The initial temperature of the hot metal was the same as boiling water. And because all I said was boiling water, we're going to have to assume that the temperature initial of the hot metal was 100 degrees Celsius. And the final temperature of your hot metal is exactly the same as the final temperature of your water, which is 31.64 degrees Celsius. Now, to calculate the specific heat of the metal, just a couple pieces of information you have to have. We know that the heat of the metal was exactly the same as the heat of the water, except the sign was opposite. So using Q equals mc delta T, we know Q, we know the mass, we don't know C, that's what we're solving for. The final temperature of the water was 31.64, and the initial temperature was 100. Well, let's do the parentheses first. So we end up with negative 11200 equals 175 C times negative 68.36. Now we want to combine like terms. I'm going to multiply the 175 by the 68.36. Well, negative 68.36. And divide both sides by the 11,963. So we end up with C is equal to 0.936 joules per grams times degrees Celsius. Good luck on the test.